Welcome everybody to this laboratory number 1 of the experimental testing for aerospace structures course. In this activity we are going to see some elastic properties of this test specimen that you can see here. It is a cantilever beam probably made by a light alloy. So our task is to assess the type of material used to manufacture this beam, and before that assess the overall validity of the Euler-Bernoulli beam model when referring to this test. The test is referred to a cantilever beam, so what we got here is the clamping device and the cantilever beam. We are going to have some transducers, strain gauges, and the measuring setup that is here. Now I'm going to detail all the components that are representative of our measuring setup.
The first item in our measuring chain is the core of the transducer, is the strain gauge. We already discussed some details of the strain gauge. These strain gauges are all contained in a box that is containing the data sheet and this set of data of strain gauges. Just to have you an idea, the strain gauge is of this size, very tiny, less than a stem, okay, and it is characterized by two connecting plates, okay, and everything should be bonded on the structure. You will see there how this is done. And the strain gauge is also accompanied by the data sheet here. During the classes we already discussed about the data sheet and information. However, here are reported the reference resistance, the strain gauge factor, the cost for the thermal compensation, calibration materials, and all other information that are needed to better characterize the measurements in terms of accuracy and in terms of reproducibility. The other item is the multimeter. This multimeter is very handy because it is possible to measure tension, currents, voltage, and resistance. Okay. In our analysis, what we got here, we have to set the measure in terms of resistance because we would like to check the resistance of the strain gauges and check whether or not this strain gauge resistance is the same as the one that is reported in the data sheet. In order to do that, we have two connecting cables. The first one is the red that we have plugged in the right position for the resistance measurements. The other black one is in the common device, and as you can see now we have almost infinite resistance. Now if you would like to have a fun just to see the resistance of the pupils, we have about 0.235, so some decimal on the ohms, okay? And that is the maximum sensitivity we can have. So by referring to what we did in the classes, that's the reason why we need a different measuring device to evaluate the change in resistance due to the strain when using the strain gauge measurements. So we have to use the strain gauge. Okay. In order to check the operative condition of the strain gauge and therefore evaluate the temperature compensation if required, we are going to use the thermocouple. Thermocouple here is the K-type. We can see in detail the hot junctions that we discussed in detail during the class. And these hot junctions with these cables are connected to the measuring device through this plug. As you can see, in order to not misunderstand the right materials to be included in your measuring chain, the plugs are completely different one each other, so that there is just one option to put your thermocouple into the measuring device like that. Okay. Once we are there, we turn the measuring device on, and therefore we will see the result. As you can see here, there is information of the type of thermocouple, K thermocouple, and now it is measuring the actual room temperature, that is about 23 degrees, 22.7. Just for fun, if I'm going to touch the thermocouple, you can see that temperature is increasing quickly. That is an evidence that I'm alive and not a robot. Okay, not that much alive because temperature is not that high, but however, better. So during your test, you are going to have this information handy so that you can check all the time what is the operative temperature that you use to compensate your strain gauge readings. The third component that you need to have is this caliper. This caliper is very useful to measure distances, to measure thickness, width of the beam in order to have the geometrical parameters of the cantilever beam. I know if you are aware of how to use this caliper, but once you have the measurement that you can have both using internal, external, width, or whatever is your geometrical shape. Then you have a double scale here that could be used both in inch or centimeters, and then you have millimeters. In order to have the information of the decimal of the centimeter, then you can use the vernier scale here. It is very difficult to see right now, but by using the vernier scale, you can have an approximation of about 120 in a dimension. Then we have the calibration weight that we are going to use to load the structure from the statical point of view. We will have several loads of this type, so that we will have different options in loading the structure. Of course, this loading will be done at the beam tip, okay, and therefore we have to take into account this loading in order to characterize when the already newly modeled the elastic behavior of such vessels. Remark about that, when we were considering this loading condition in the classes, we were referring to what is theoretical loading condition, but actually because we are using this kind of calibration weight, it is not clear what is the point of application of this load. It could be either this lower surface attached to the beam or the upper surface if you use the weight and mass in the reverse position. So it is up to you discussing the effect of the uncertainty of the positioning of the loading in your beam while writing your report.
The strain gauge measurements is based on this strain gauge measuring device. It is a very old one, but it is very up and running, so it is very useful, especially for field operations. This strain gauge is composed by many knobs, many plugs, many switches. Now I'm going to detail some of them. The first one is the on-off level. So we have to remember to turn the level off or on according to our operation. Then there is the mode switch, in which we can have the information of operation, test for batteries, and other switches that are not of our interest. Sensitivity switch here, you can change between different values from 50 up to 5000, and that is telling us what is the maximum value this scale is going to measure. So that is the sensitivity. Of course, as already said during the first class, you have to know what is the measuring range of interest, and therefore you start by selecting the proper value of the sensitivity using this switch. Then we have the gauge factor switch, in which we are setting the right strain gauge factor corresponding to our strain gauge. As you can see, the values are ranging from 1.75 approximately up to 2.20. Okay, and as you remember, during our classes we already discussed that the average, the typical value for the strain gauge factor is about 2, and that is the reason why. So you have to select using the switch the strain gauge factor that is corresponding to your strain gauge. Then we have a number of plugs. You have to look at these plugs from the column point of view. So we have 1, 2, 3, 4, 5 columns of plugs. Okay, each column could be selected using the switch from column number 1 to column number 5, as you can see here. Okay, each column of plugs allow us to connect your strain gauge to the measuring device. By using these plugs, you can have the quarter bridge configuration, half bridge configuration, and full bridge configuration. Indeed, this measuring device is an actual Wheatstone bridge measuring circuit. If you remember the equivalent electrical circuit of the Wheatstone bridge, then you compare that to the actual Wheatstone bridge. Okay, as you can see, there is a difference, more complicated and more electrical circuits to consider. Okay, but for our purposes, the equivalent Wheatstone bridge circuit that we discussed together during our classes is perfectly working. Okay, this is the more detailed circuit representation of the actual measuring device. Then, as I just told you, we have to consider the plugs for several type of connection. So we have the chance of having the full bridge circuit, as you can see here, the half bridge circuit, and quarter bridge circuit. And we can have that by using different wirings. Okay, the wirings are connecting in a different way the plugs of each column. Okay, now we are going to enter some details on the measurement itself. The first step is to check the resistance of the strain gauge in order to see if there are some short circuit, if the electrical connection are properly carried out, and therefore we can rely in the measurement. So what we have to do now is to check that the resistance is the same as the nominal value that is reported in the data sheet, and that nominal value is 120 ohms. So what I have to do now is just take the wirings that are connected to the strain gauges, then we connect this wire to these terminals. Okay, then wait a few seconds, and as you can see, the actual resistance is about 120 ohms. It is not perfect 120, it is something different. That's because of the effect of the connecting cables that are pure acceptable. Once we done that, we check that the connections are properly carried out, and therefore we have just to keep an eye on the room temperature. That is done just by checking your thermocouple measurement, and as you can see, the actual room temperature is about 22 degrees, 29.9, 21.9, 32 this moment. And this information should be always updated according to possible changes in the room temperature. Now I put this thermocouple just here in order to have an eye always on the temperature. The next step is the wirings of the strain gauge. In order to do that, I recall you the wirings, and these wirings are the wiring is referring to the bottom connection, that is quarter bridge configuration, okay, that uses a minimum number of wires. So what we have to do, according to what we have here, we have to connect the strain gauge to terminals called D and quarter, and then short circuit the quarter with terminal F. Okay, and that is what we are going to do right now. So the first is connecting the strain gauge with terminals D and quarter. These are the terminals of the strain gauge at the beam root over here. I'm using the first column, so first channel, and therefore I plug the connector to terminal D, and then I plug the remaining connector to terminal 1/4, and then by using these additional wiring, I'm short circuit terminal quarter to terminal F. F. Okay, and that is the completion of the wirings of the terminal of the strain gauge in a quarter bridge configuration. Now what we have to do is start the operation of your measuring device. We select channel number 1 because it is the one to which we attach all the strain gauge wirings. Then we select the right gauge factor. In our case, the strain gauge factor is 2.1.
We refer to this display and the series of knobs. If you can see better, on top of the knobs there are some numbers. These numbers are very important when taking the measurements. Okay. Before starting, of course, it is mandatory to check whether or not the battery is okay. So we select the switch to battery test, and then we switch to on position with the selector. And as you can see, the arrow is going into the battery working area, which is region for the good battery. We are okay with battery, then we switch once again to operations. Okay, and how can we perform the test? We perform, as I told you before, just by considering this screen, this display, and the app. Please note that the display is also having a mirror behind the middle here, and that is because by using that mirror we can reduce as much as possible the parallax error. So that once you are taking the reading, you have to be normal with the screen here, and this mirror helps you to prevent or to be as much normal position as possible, and therefore prevent any possible parallax error. In order to take the measurements, you are going to use two methods. The first one is called the deflection method, and the second one is called the zero method. Both of the methods, as you are aware about, are starting from the balancing condition. So we are going to balance our bridge, our wisdom bridge, as a first step. Let's start with the circuit, and as you can see in the operating condition, by selecting the first column with the wirings connected as the quarter bridge configuration, it's going to have whatever position it is. So by rotating the knob so that the arrow goes to the vertical position corresponding to 0, we are now changing the internal equivalent resistances so that the balance condition for the wisdom bridge point of view is satisfied. So I start from the left and then knob, then go to the right knob, because these knobs are characterized by increasing sensitivity. So start with the left one, so I rotate counterclockwise, and at a certain point the arrow is moving totally from right to left, as you can see. So I move one step backward so that the arrow is to the right. Then I start rotating the other knob with less sensitivity, and and then rotate in order to move the arrow to the center position. So rotating that counterclockwise, 1, 2, too much, so 1 there. Then move to the third knob, okay, and then once again rotating that counterclockwise so that we try to move the arrow to the center position, rotating, almost there, and then the last knob is allowing the fine tuning of the measurement, okay, so that we are okay. Now we have balanced the distance bridge, the starting point for all the measurements, and what we have to do is apply the calibrating weight at the DT. As you can see, just by touching with my finger and DT, we have a corresponding movement of the arrow of the scale that is representative of the strain that these strain gauges is. If I move down the beam, we are having a positive deflection, traction. If we are moving up, we have a negative deflection, compression. Please note that also it is very important to set the proper value of the sensitivity. If you check here this knob, the sensitivity is set to 200. So the maximum value of the strain that could be measured using this selection is 200 minus strain. Okay, that is if you check the number of subdivisions. Each subdivision means the words 8 microstrain. Now we are applying the load to the tip like this, and here. Okay. Now deflection method. What we can say is that we have just to take the readings on the scale, and that is the value of the strain with the sign. So in our analysis, in our test, by applying that weight, the reading is 48 plus half of the subdivision, so we have 52 microstrain. Now, what we have to do, and that is the deflection method, what we call deflection method. Just take the reading of the scale once we balance the distance bridge. The zero deflection method is requiring us the balancing of the visual circuit also under the loading condition. Therefore, what you have to do is take this number, write down the value of this number. In our analysis, we have, please take note of that, we have 5, 0, 0, 5, 1. Then we recalibrate this bridge so that we move back the arrow to the zero condition. Once we balance back the distance bridge, that means once again the arrow is put back in the upright position, pointing to the zero value, then we have to take the reading of the number. So we got 5009.4. Now, if we take the difference between the previous reading and this actual reading, what we got is the difference equal to 53. That is our new reading. As you can see, we have 52 microstrain for this deflection method and 53 microstrain for this zero deflection method. There is a slight difference, and that is because we have two different approaches, and there is some uncertainties that comes from the actual readings, okay, both from this display and from the other display, but they are fully compatible. 52 microstrain compared to 53 microstrain. Please note the actual temperature, the room temperature, is once again 29.9, so it has not been changed so far.
and the temperature could be considered equal to 22 and that's it. Now, what you have to do is, if you were here in the laboratory, is to take the measurements by your own by changing the strain gauge position, okay, and then doing that several times in order to have a representative statistical population. It is proved that if you take 10 measurements per each strain gauge and per each measuring method, zero or deflection, you have a quite wide and relevant statistical population to take to consider all the possible statistical evaluation of your data, so that you can have an average value that is input, root mean square that is giving you a sort of information of the uncertainty of your measurement. Now we are going with the help of our assistant. We are going to have the measurements for you. We are going to share the data with the file that could be easily read by MATLAB or other very easy software. Just one comment. The first comment is that first you have to be very, very careful in evaluating the distance of the load that is the calibrating weight with respect to the clamping position. Therefore, you have to better evaluate what is the mean of this clamping condition, because as you can see here, it is not an ideal one. We are not sure about the starting point for the clamping device, because we have a physical dimension that is not very, very defined. We have also to take care about the positioning of the different measured points, the distance from, once again, from the clamping part, okay, of the strain gauges. Okay. So what you have to do is to evaluate the trend, the distribution of the strain that you measure over the beam. You have, once again, one strain gauge at the very position very close to the clamping end, then at about the midspan in the upper surface, then you got another one in the lower surface, and then you got another one at almost a 3/4 position with respect to the midspan at the lower part. Okay, so you have 4 strain gauges that could be used to characterize the distribution. If you know something about the Euler-Bernoulli beam model, you can easily characterize these strains according to the bending distribution, and then you can check whether or not you are in agreement with the Euler-Bernoulli beam. And once you know that, and because you know the different value of the strain, you can easily estimate the Young modulus of this light alloy material that is used to manufacture. Please consider all the details that we discussed together before doing the class, so that you get all the information concerning the statistical evaluation and some other discussion that we can have. I hope that you can enjoy the measurements. I hope that you can even more enjoy the data analysis that you are going to perform. Please write all your findings and all your discussion in your laboratory activity record number 1. Thank you.